morning, everyone. My SIParCS project is implementation of PD solvers using RBFFD, radial basis function finite differences on multi-CPU GPU systems. So I'm Srivatsa. I'm a master's student in computer science at the University of Utah. So I would like to thank my mentors, Dr. Flyer, Dr. Loft, and Dr. Kumar for their support and guidance, and my co-intern Tuan for the interesting discussions we had, and also his help. And I thank my student assistants, Priyanka, Rashmi, Harish, and Amog for their help, and the SIParCS program for giving me this wonderful opportunity. So the outline for today's talk is this. So first I would go over introducing the problem that I worked on, the motivation for the project, and then I'll go over the details of the RBFFD PDE solver, then its multi-CPU GPU implementation, and then I present the performance results that we got on both the standalone hardware as well as the cluster. Then in conclusion, I present the observations from the results and then discuss the future work. So the problem I worked on is an advective transport of a scalar quantity. So advection is a phenomena where a conserved quantity is transported by a fluid due to its bulk motion. And the examples are the transport of pollutants in atmosphere and transport of silt by the downstream river flow. So the current problem is a linear hyperbolic partial differential equation. And in this equation, the u and v are the velocity vector fields, and the psi is the scalar field. So I just want to show you a small visualization video. So this the substance moves in the fluid in a whirlpool motion and then comes back to its state. So this is how it looks in the visualization. So what we try to understand is how its scalar field is affected by the velocity vector fields in space and time. So we have many numerical methods to solve PDEs, and we use the radial basis function finite differences method. Why? It is a meshless method as compared to the traditional finite differences and finite elements, and it's well suited for the scattered node layouts in n-dimensional space. And also it extends to the higher dimensions without much increase in the complexity, and also stable for large time steps. And we have two different RBF methods, a global and RBF-FDs, which are local. So the difference is that they use local approximation as opposed to the global approximation, using all the nodes in the domain. So that means that they grow at a smaller rate as compared to the global RBFs. But the challenge here is to parallelize and scale them on HPC systems. So if you look at a surface represented by this point cloud, so the red dots there is a stencil. So the local approximation is done in this stencil. So the boxed point is the stencil center. So the approximation at that point uses the values from the other points in the stencil. So the RBFFD solver has two main stages, the pre-processing and then evaluating solution. So in the pre-processing stage, once we have the surface that's represented by the set of points, we generate these stencils using a k-nearest neighbor search algorithm, and then we compute the RBFFD stencil weights in these stencils, which is by using a direct solver on small full linear system. So once that stage is done, we then solve for the solution. And then if the PDE is time dependent, then we time step. So in this problem, we use the Runge-Kutta 4 for the time stepping. So and also in the project, we focus on parallelizing the second part of the solution, which is the second stage. So we parallelize this on GPUs, whereas we do the pre-processing on CPUs. So the motivation and the challenges for this project are, since we are working with the scattered nodes, the partitioning and the communication are challenges here. So it is really difficult to find a partitioning scheme that would give us good load balancing as well as minimize communication, because we are working with the scattered nodes as opposed to structured grids. And also, in contrast to the finite difference methods, we have large stencils. That means we have a lot more computation. So and the future goal is to accommodate the adaptive node refinement, where we restructure the points in the domain for more accuracy. So that means we might have to do the pre-processing too after every refinement step. That would add a lot more to the computation. So so these are the challenges as well as the motivation for this PD solver to be parallelized on multi-CPU GPU systems. So the development process is started with a MATLAB code for the PD solver and then implemented a serial version. We fairly optimized it, but we didn't do the exhaustive optimization. My co-intern Juan did his optimization on both CPU and GPU, which he'll discuss in tomorrow's talk. So after that, as I mentioned, we parallelized the solution advancement stage on GPUs, on single GPU. And then I worked on the partitioning schemes for the distributed implementation. And once that is in place, I merged both of them for the multi-CPU GPU implementation. So the workflow for the implementation, we used a tool called Metis that I'll discuss in detail in the next slide. For the partitioning, it is a graph partitioning tool. So once we do the partitioning, every compute node should have the information. For example, the information that it's sharing with its neighboring nodes. So we communicate all of that for every node. So once all the data that's required for communication is in place, we then compute the stencils and RBF FD weights, which is the pre-processing stage I mentioned on CPU. And then the time stepping is done on the GPUs. So in the time stepping, the GPU has to communicate in the multi-CPU GPU version. It has to communicate with the CPU for it to talk to its neighbors to communicate the results and then proceed for the next step. So once this process is done, in the end, we verify the results by aggregating all of them from the different compute nodes. So coming to the domain partitioning step, we used a tool called Metis that's developed by University of Minnesota. So it is a graph partitioning tool with its algorithms to partition graphs efficiently. So what we do is, once we have the domain of points, we convert this into a graph that, using the k-nearest neighbor search, because we are working with the scattered points. So we don't really have the information of the neighbors available since the domain is scattered. So we use that to generate the graph. That's the input for this partitioning tool. And once we have the graph, the two partitions and the visualization for the partition looks like this. So the different colors represent the different partitions. So each of this partition goes to one compute unit. So each compute unit might share some information with its neighbors. That's approximately, it depends from 2 to 5 in this case. So we have different, the points in the domain are in different coordinates. So I just have a sample here because these are both structured and unstructured. So in the structured case, we have the Cartesian and hex, which are relatively easy to deal with. But this project, I mostly worked on the scattered nodes, and all the results are presented for the scattered node layouts. So coming to the implementation, the interpartition communication is handled by the CPU using MPI. So as I mentioned, we implemented this time stepping schema on the GPUs. So once we have the information for communication in place for the CPU, so it starts its work by offloading this time stepping part onto the GPU. So if you look at it in RK4, there are 4 increments. So at every step, so the CPU gives the information for computation to the GPU, and then it processes and then gives back the result to the CPU, and then it communicates the data that's required by its neighbors. The CPU does that, and then gets back what it needs from its neighbors, and then it gives, for the second iteration, it gives the data for the GPU. So as we see, there is a lot of communication that's involved in multi-CPU GPU case, so which really affects the performance, which I'll talk in my results slide. So if you look at it, there is, for every increment here, that the CPU has to talk to GPU for giving the information for computation and then get back the results, and then communicate that back to the other CPUs. So the communication really hits hard here, the performance. So we tested the implementation on both standalone as well as the cluster hardware. So the standalone configuration is it has two CPUs, the Haswell Intel Xeon E52630, each with 8 cores, and then 2 GPUs with GTX 980 Maxwell. And on cluster, the Caldera, each node has 2 CPUs, the Sandy Bridge Intel Xeon E52670 with 8 cores, and then the GPUs are Tesla K20X. So first I have the single CPU versus single GPU versus multi-CPU results here. So what we observed was, for the time stepping part, as compared to a fairly optimized serial code, we have really good speedups with single GPU. But as I mentioned earlier, the communication hits hard for the performance of the distributed implementation here. So the MPI 8 is 8-core CPU implementation, and then MPI 16 is using 16-core. This is on the standalone hardware. So on the y-axis, we have the speedups, and the x-axis, we have the number of points. We tested for 4 different problem sizes. So it starts with 2,500 points, all up to 160K. So we achieved the speedup of the max speedup of up to 35x for a problem size of 160K. And then for the multi-CPU implementation, we have like really less speedups as compared to the single GPU. And then we have the similar results on the Caldera too. So on Caldera, we have additional 32-core implementation here. The speedups are better compared to the smaller ones, but still, as compared to a single GPU, the speedups are not that great because of the communication overhead that we had. So next, coming to the multi-CPU GPU results. So we have 4 implementations here. The first one is a single GPU, and then the MPI CUDA 2 is using 2 CPU cores and then 2 GPUs, and MPI CUDA 4 is 4 cores and then 4 GPUs, 8 cores and 8 GPUs. So we had up to 45x speed up using 8 GPUs, but then that's not that's just like over 10x speed up over the single GPU version. So still the 4 and 2 GPU implementations run slower than the single GPU. So the reason for this is there is a lot of communication involved between the CPU and CPU GPU, which takes significant amount of time. So that really affects the performance of this distributed implementation. So in conclusion, we have a multi-CPU GPU version implemented for this RBFF-DPD solver, and we achieved like 30x speedups with the single optimized GPU implementations, and then up to 9x speedup with the multi-CPU implementation. But we need to look at the communication for the multi-CPU GPU implementation and then reduce that to achieve good speedups over the single GPU. So overall, single GPU is really well suited for the time stepping part in this problem. And in the future, we would like to explore different techniques that would minimize this communication. And also for the adaptive node refinement, we might have to do the pre-processing after every refinement step. So we would also like to do that on GPUs, the KNN search, and computing the RBFFD weights. Thank you. Any questions?
Any questions? Yeah, go ahead.